Good afternoon, everyone. So this session will be a database developer deep dive for the in-memory OLTP feature that we're introducing in SQL Server 2014. Now, I will be walking around a little bit off the podium here because there are very bright lights shining in my eyes when I'm standing up the podium, and then I cannot see you guys, and I do like to interact a little bit. So also, please, during the session, when you have any questions, when anything is unclear, please let me know. So yesterday, I gave an overview session about the feature. So can you give me a show of hands of who attended the overview session yesterday? Okay, so it looks like most of you did. So most of you should by now be a bit familiar with the feature. And for those of you who are not, I will give a kind of brief recap of the main aspects of the in-memory OLTP feature that we're introducing in SQL Server 2014. My name is Jos de Bruin. I'm a program manager with the SQL Server team and been working on this feature for the last couple of years. So what is SQL Server in-memory OLTP? Just to give you a brief recap. It is a feature that boosts the performance of OLTP workloads. That is the main tagline, I would say. And it does that by using new memory optimized technologies. So first off, we have kind of 4 pillars. I want to go through each of these pillars. So the first pillar is we have memory optimized data and index structures. So we get rid of concept of pages. We don't have B trees. Instead, our atomic storage unit is a single row, and you can navigate to rows through memory pointers. By getting rid of pages, we also get rid of page latching, for example. And by navigating our in-memory structures using memory pointers rather than navigating trees and navigating pages, we can also more efficiently access the rows that are in memory. So, for example, we don't have anything like a buffer pool or anything like that. Also, an important point I want to reiterate is that indexes on memory-optimized tables exist only in memory. They do not exist on disk, and they are not logged. This gives you also some space savings. Now, the second main aspect is that we want to optimize execution of business logic. And we do that by compiling T-SQL stored procedures to machine code. So we take a T-SQL stored procedure, create a DLL. This can be executed much more efficiently. So you need fewer CPU instructions to execute the same queries, execute the same business logic. Third, our data structures are completely latch and lock free, and also the algorithms we use for transaction processing don't use any locks, don't use any latches. This is great for concurrency. So if you have concurrent transactions, they don't need to wait for each other. One important thing to keep in mind is because we don't use locks, still you can have a situation where 2 transactions come in. They want to, for example, update the same row. Right? And we do want to prevent inconsistencies in the database. So in that case, instead of having one transaction wait for the other through locking and blocking, instead we let the second transaction that comes in fail. And this will need to be retried. And I will go into some detail later on as to now how this works exactly and what the ramifications are for your applications. Lastly, the feature is fully integrated into SQL Server. So you access memory-optimized tables and natively compiled stored procedures just in exactly the same way as you would access regular plain old disk-based tables. So through the same connectivity layer, same T-SQL, same familiar T-SQL, you can use the same familiar development tools, the same management tools, Management Studio, and also things like backup restore and HA are fully integrated. So if you have always on setup, that will just work with the new memory optimized tables. So now in this session, I especially want to go into detail of now what these tables and index structures are, how you create them, how to use them, and how to access them using natively compiled stored procedures and also the existing interpreted T-SQL. And finally, like how the log-free and ledge-free aspects of the transaction semantics interact with your application. So this is, that's basically these three things. So core thing is your memory optimized tables and indexes, how to specify them, how to use them, what they actually look like, how to access them from your application, and ramifications of the transaction semantics in your application. So first of three, of course, memory optimized tables and indexes. So this is a create table statement. Now, a lot of the syntax will look familiar for you, like we have a create table, we have some column specifications, we have some constraints here and there, and some data types that should look familiar, but also some keywords which will not be familiar, and I want to walk you through these. So first off, you specify that the table is memory optimized through this keyword, memory optimized. You say memory optimized equals on for your table. By specifying this, you say this table is memory optimized. So it is, for example, not possible to change a table to be memory optimized. Now you need to specify when you create the table that it is going to be memory optimized. It's a create time option for your table. So if you want to, for example, replace a disk space table with a memory optimized table, what you would typically do is you rename the disk space table, create a memory optimized table with the original name, and then do an insert select to move the data. Second option I want to mention here is durability. Now this option is, this setting is optional, so you don't need to specify it. And in fact, the default, if you don't specify it, is that durability is schema and data. That means both schema and data are durable, are persisted, and after server crash, you will get them both back. This is the default kind of durability guarantees we give for any table in SQL Server, or typical tables in SQL Server. The other option is to say this is schema only. In that case, only the schema is persisted, and then you have a non-durable table that is not logged, which can be useful in some cases. For example, if you have some transient data like session state that you don't need to keep. But in most cases, you will want to use schema and data because you want to make sure your data is always available. Then this is also a new aspect, the non-clustered hash index. So a hash index is a new type of index which at this point can only be specified with memory optimized tables. And actually also in CTP1, these are the only indexes supported with memory optimized tables. And hash indexes are especially very good for point lookups. So usually you will need only like 2 or 3 hops to get to your row when you use a hash index. I will talk a little bit more about what these hash indexes look like in a minute. And I mentioned in CTP1 we have only non-clustered hash indexes on memory optimized tables, which are good indeed for point lookups, but not for range scans. So you cannot scan a range like maybe you want all values between 1 and 100. No, you will need to scan the entire table and then apply a filter afterwards. We will, in CTP2, also introduce non-clustered indexes on memory optimized tables. These will support range scans and order scans as well, but will not be as efficient for point lookups. So then it will really depend on what you want to do in your application, which type of index you want to specify. If you do only point lookups on the column or this set of columns, you want to specify a hash index. But if you do mainly like ordered scans or range scans, you want to specify the non-clustered index. Also, one thing to note is here the bucket count. This is a required option with hash indexes that specifies how many buckets there are going to be in the hash table. And I will show you the structure in a second. Another thing that we introduce with SQL 2014 is specifying an index in line with the create table statement, secondary indexes specifically. We already supported primary key indexes. So you can specify, even with disk-based tables, you can specify your secondary indexes in line in the create table statement. And in fact, with memory optimized tables, you need to specify all your indexes with the create table. You cannot add indexes later on, because when you create a table, we compile this into a DLL, and the index structures and the methods for accessing the indexes are built into the DLL. So this is an example of a secondary index. This secondary index is specified with this column. You can also specify a secondary index separately below the column definitions, the same way you would specify a constraint. And then you can also specify an index on multiple columns. So we don't specify only single column, but we support also multi-column indexes. So this is roughly what happens under the hood when you issue a create table statement. So you issue the create table DDL, then SQL Server generates code based on the DLL and compiles this, well, based on the DDL, and compiles it to a DLL. So then we have this DLL, and this is then loaded into memory. And only then, after this finished, control is given back to the client. So you always have this DLL, and we have this DLL for efficient access to the table and index structures, because the index structures and also the information about the columns in the table and how to extract the column data from the rows is all built into this DLL. So I promised you I would talk a bit more about hash indexes, so now I will. So a hash index is, in the end, a set of buckets. Right? So in this case, this is a representation of a hash index with 8 buckets. So this is like a hash index with bucket count 8. And these buckets are just, in memory, they are just 8-byte memory pointers. So you can view this as an array with memory pointers. So you have here a number of slots in this array, 8 slots. At slot 0, there's a memory pointer. At slot 1, there's a memory pointer, etc. And then SQL Server has a hash function built in. This is a random function, but it always maps the same value to the same slot. So it's a random function that maps values, maps index key values to slots in the slot array. So you can think about, well, if you have strings, for example, this could be an example mapping. This is just an illustration. I'm not sure if the actual mapping looks like this, but for the sake of argument, let's say the mapping looks like this. So Jane is mapped to slot 0, Prague and John are mapped to slot 2, Susan is mapped to slot 3, and Bogota and Beijing are mapped to slot 5. This is example mapping. And what you can see is that not every value is mapped to a separate bucket. It's mapped to a separate slot. So it can happen, because it is a random function, it can happen that multiple values are mapped to the same slot. And the smaller your hash index is, the higher the likelihood that multiple values are mapped to the same slot in that array. So, and when this happens, when multiple values are indeed mapped to the same slot, we talk about a hash collision, which means that in this case, like rows with the same index key, or sorry, rows with these different index keys will need to be mapped to the same bucket in the hash index. Do we have something here? Yeah. So that is kind of the basics of a hash index, and I will show you now how this interacts with the rows in a table, and also what the rows in a table roughly look like. So rows in a memory optimized table contain of a header which has like a timestamp and a number of index pointers. We'll show you through an example how this works. And after that, it has the column data. So my timestamps are going to tell me at which point in time this particular row is valid in the database, because each transaction works with a particular timestamp, and it uses this timestamp to determine which rows are visible at any given time. Now, I have here 2 sample rows. So, as I said, rows are the atomic storage units, so they are not organized in any other structure. So we just have rows in memory. In my example, I have 2 rows, Jane, Prague, and Susan, Bogota. If we look at the timestamps, Jane, the row Jane Prague is valid in time 50 to infinity, which means that it's visible for every transaction that started at time 50 or higher. And this timestamp is just an increasing integer. You know. And Susan Bogota is visible to every transaction with time 90 or higher. And now to access these rows, if I have just these rows, I cannot access them. So in fact, I always need to have an index. Every memory optimized table needs to have an index in order to be able to access the rows in the table, because, like I said, they're not organized in any other structure. So I have here a hash index on name. As we saw, Jane is mapped to the first slot. Susan is mapped to the 4th slot. So these slots are memory pointers which points then to this individual row. So this one points to the row Jane Prague. This one points to the row Susan Bogota. And now, in this example, I have a secondary index. Well, they are both secondary indexes in some sense, or primary in some sense. I simply have 2 indexes on this table here. So my second index is a hash index on city. And as we saw, Prague was mapped to the 3rd slot and Bogota to the 6th slot. So this slot for Prague contains a mapping to this row here for Jane Prague, because Jane's in Prague, and the 4th one to Bogota, because Susan is in Bogota. Now let's see what happens if we do some operations in the table, some DML. So let's say I want to insert a row, John Prague. Okay, so I write this row to memory, and let's say this was at time 100. So the row is going to be valid from time 100 onward. So John in Prague. Now, John happens to map to the 3rd slot in the index, so there's going to be a pointer now to that row from John Prague. And now, as we saw before, like Prague is mapped to the 3rd slot here, but this 3rd slot already points to Jane in Prague, and well, the slot has only one pointer. So what happens now? So what happens is that this row here has chain pointers. So it has, for each index the row participates in, there is a pointer in that row for the next row in the index. In this, it initially did not have a next row, but now it does have a next row, and the next row is John in Prague. So if I want to now do a seek on city Prague, I'll jump into this index, I find my first row, I return it, and then I see, oh, there is another row in this index, so I return that second row as well. Okay, so the next operation, after insert, delete. Right? So let's say at time 50, we want to delete the row Susan Bogota. So we want to delete this bottom row. Now all that happens in this case is just we mark this row as no longer visible as of time 150. So we say this row now has an end time. it is only visible between times 90 and 150. It's not visible afterwards. Because there might still be transactions that need to see rows that are visible before 150. Now, let's see what happens with an update. So I want to update John Prague to John Beijing. So John is moving from Prague to Beijing. So I need to update that row. Now, how do I do that? This is implemented through a delete followed by an insert. So I first delete the row John in Prague. So I say, hey, as of time 200, this row is no longer valid. So you're no longer allowed to see it. And I insert a new row saying that as of time 200, John Beijing is the valid version of this row. So every new transaction that comes in will skip this row and will just look at this row. And there will be now a pointer from the old row to the new row because John still maps to the same slot in the index. And, well, what we have actually now with Beijing is we have a bit of a problem because Beijing maps to the slot 6, but also Bogota maps to the slot 6. So we have here a hash collision. Now what happens is that we just add the row to this particular bucket in a similar way as we did when you have the same key. So now there's going to be a pointer from the row Susan Bogota to the row John Beijing. So the disadvantage of a hash collision, of course, is that when you seek on Beijing, Beijing is mapped to this bucket, then you go to this row, but you will need to skip it because it doesn't match Beijing. So you need to potentially navigate a number of rows before you get to the right row. Therefore, it is important to reduce the chances that there are hash collisions. So that is where the bucket count comes in. So usually you want your bucket count to be between 1 and 2 times the number of unique index keys that you have. In that case, there's a sufficient low chance of hash collisions. And if you have just a couple of hash collisions, that is fine as long as you don't have massive hash collisions in your index. So then the last thing I want to touch on for the table and index structures is garbage collection. So by doing all this DML, by doing deleting and updating, we are accumulating some old rows, some stale rows, like John Prague between 100 and 200, and Susan Bogota between 90 and 150. And let's say the oldest transaction in my system started at time 250. That means that all these old rows, nobody needs them anymore. So I might as well get rid of Susan Bogota and John Prague. So therefore, the system has a garbage collection process, which once in a while comes in and cleans up the old rows. And in tomorrow's breakout session about DBA concerns, we'll get into garbage collection a little bit more. So essentially what garbage collection does, it just takes out these rows and it reorganizes the index pointers to such that, whereas the pointers match the original hash mapping. So this is now going to be my new state of the database. As of time 250, we have Jane in Prague and John in Beijing. Okay. So that is kind of the basic tables and basic tables and indexes. Now, because we do compile memory optimized tables to DLLs, and we have these novel index structures and table structures, we needed to build all these things from scratch. And we did our best to support as much as possible the T-SQL service area for tables in SQL Server. And of course, there's always limited time and limited resources, so we could not support all features that are available for regular disk-based tables. So, for example, we do not support DML triggers or exotic data types like XML and CLR. And we have limitations on the size of our rows. So rows are not allowed to be more than 80, 60 bytes. And we don't store any data off row, and we don't have any particular lob storage. So lob types like varchar max and var binary max are not supported. And also there are certain constraints which as of yet we do not support. So foreign key, and check constraints, not supported. Identity, not supported. And also schema changes and add remove index are not supported. So if you want to change the schema of your table by, for example, adding a column or changing a data type, or you want to add or remove an index, you will need to drop and recreate the table. These are limitations in SQL Server 2014. Of course, in the future, we will definitely remove some of these limitations, but this is what we have for now. So the next thing I want to touch on is how now to access these tables and indexes. So you've created your tables, created the right indexes on the tables, and now you want to access them from your application, do some DML, do some processing there. So we have this new natively compiled stored procedure, where we take a T-SQL stored procedure and compile it to a DLL. And this is what the syntax looks like. So, and we in fact have a number of options which are required for natively compiled stored procedures. So first off, you need to say actually that this is a natively compiled stored procedure. So you use the keywords with native compilation to specify that the stored procedure is native. Then we also require each native stored procedure to be schema bound. So we don't want the schema to change underneath. For example, we cannot tolerate like all of a sudden a table dropping underneath because we want to optimize the access paths as much as possible. So the access to the table DLL is hard-coded in the stored procedure DLL. So we cannot tolerate this just disappearing. So therefore, it needs to be schema bound. Then we also require you to specify the execution context. So you need to specify under which user this stored procedure is going to run. So we support owner, self, and also using a particular user here. We don't support execute as caller. The reason is that we don't want to do permissions checks with each invocation of the stored procedure, which is what you would need to do with execute as caller. Instead, what we like to do is just do a permissions check when the stored procedure is created and then just execute without rechecking permissions all the time. And only when permissions on the server are changed, then we recheck. But this is sufficiently rare that we can take that overhead at that time. We want to, of course, always optimize execution as much as possible. Then we have a new construct here, which is, I think it's a nice programming construct, but it's also a required construct in natively compiled stored procedures, and that is the atomic block. And you specify that through a begin atomic. And this is actually in the ANSI SQL standard. So with this, SQL Server is getting a little bit closer to the ANSI SQL standard. But unfortunately, as of yet, begin atomic is only supported in natively compiled stored procedures. But the way to think about an atomic block is that this is an atomic set of operations. Either the whole block succeeds or the whole block fails. And in addition, what it gives you is that if there is no transaction already running, if there is not yet a user transaction, the atomic block will also create one. So if you have no user transaction when executing a stored procedure, the transaction is created at this point, at the beginning, and it is committed at the end, unless there is an error in the stored procedure. So if the stored procedure throws an error, in that case, the transaction is rolled back. So you don't need to, you as a database developer no longer need to care about when to commit or when to roll back a stored procedure. It's just handled through the typical error mechanism. So, and if there is already a stored procedure, sorry, not a stored procedure. If there is already a transaction when you invoke the stored procedure, then it creates a save point in this transaction. And if there is an error in the stored procedure, then the transaction is rolled back up to that save point. And if then in the user transaction you catch the error, you can just continue execution of that transaction. Then another aspect here is because we compile the procedure into a DLL, we don't want to depend on any session settings at runtime for execution, because we want to make execution as fast as possible. So we fix the session settings always at create time. Now the user can specify a number of session settings as part of the atomic block, and actually there are two settings are required. Transaction isolation level and language are required. And a number of other session settings, such as ANSI nulls, ANSI padding, we pick a default for you. Like ANSI nulls are always on, ANSI padding always off. So when you create a stored procedure, the process is fairly similar to creating a table, that there's one more step. So you as a user executes the create procedure DDL. Then we run the stored procedure through the query optimizer to get an optimized execution plan for the query. So we leverage the SQL Server query optimizer to make sure we have the best possible plan, or an approximation of the best possible plan. And based on this query execution plan, we again generate code, we generate C code, compile this to a DLL, and load this into memory. And only at that point is control returned to the client. So there are these two ways to access memory optimized tables. There is the traditional interpreted T-SQL access, which is just any typical old ad hoc batch or a traditional stored procedure. We refer to this as interpreted T-SQL to contrast it to natively compiled. And there is, of course, the natively compiled stored procedures. And there are advantages and disadvantages of using the one or the other. So with interpreted T-SQL, you can access both memory optimized tables and traditional disk-based tables in the same query, in the same procedure, without limitations. Whereas in natively compiled stored procedures, you can access only memory optimized tables. So if you need to access both types, you cannot use a natively compiled stored procedure. But of course, what you can do is take a regular interpreted T-SQL stored procedure, and for some piece of logic that you really want to optimize inside this procedure, you create a separate natively compiled stored procedure and call this natively compiled stored procedure from your interpreted procedure. Now, of course, the natively compiled stored procedure is more optimized, so it will generally execute faster, although there are also some caveats there, because we mainly optimize for OLTP type queries. So if you have like more reporting style queries, cases where you, for example, use hash joins or something like that, then a native proc would not be the optimal choice. And also inside natively compiled stored procedures, there are some limitations on the T-SQL that you can use. For example, we don't support OR in the where clause, we don't support outer joins, and several other limitations. We don't support all built-in functions. So that's also something to consider. So if your application logic requires some of these T-SQL constructs that are not available in native procs, you will need to use an interpreted proc. So when to use it? So typically for your native procs, for OLTP style operations that you really want to improve performance and really want to optimize. And also you need to think about it like this. You use your natively compiled stored procedures for this business logic where you are willing to invest in making it faster. Because Well, because of the limitations we have on the T-SQL surface area, probably your existing procs will not fit this exactly. There's always going to be some things which don't work exactly. So you will need, depending on what you use exactly, you will need to put some effort into working around the limitations. But the potential benefit is also very big, as you have seen in some of the demos. But yeah, it is always good to be realistic there. And there's always this trade-off, right? If you want to go very fast, you need to work harder. It is like that. Scenarios when interpreted T-SQL is particularly suited are for things like ad hoc queries or reporting style queries. And also if you want to speed up migration of your app, like we typically suggest if you want to migrate your application to use in-memory OLTP, as a first step, you will migrate your tables and then use interpreted T-SQL access to see if you get any benefits, what kind of benefits you can get. And only then will you start looking at your stored procedures and see which parts you want to further optimize. So I have a small demo here for, oh, I think I need to log in. For creating tables and stored procedures and accessing them. So I have here my SQL Server instance. I'm creating a database. And so as a first step, what I need to do to be allowed to even create memory optimized tables is I need to add a memory optimized data file group, and I need to add a container to this file group. These containers are very similar to FileStream. One thing to keep in mind is that you do need to specify always the container location, which is just a folder on your machine. And you can do this also through a GUI provided by Management Studio. Now I have here my create table statement. So typical create table, typical table with a bunch of columns. I have here 3 columns: order ID, order date, and order status. This should look all very familiar. Constraint primary key, and then I need to specify here that I'm using a non-clustered hash index with my primary key because, well, we don't have clustered indexes for memory optimized tables. The concept simply does not apply because the table rows are just there in memory. They are not clustered in any way, and also all indexes are actually covering. So I have this. Non-clustered hash index, yeah. So then let me go ahead and create this table. Oh, I forgot to change my database context. So I'm now creating a memory optimized table in the database I just created. And now I can also, for example, query the catalogs to see what kind of tables I have. As you can see, I have one user table here, which is memory optimized, and the durability is schema and data, which is the default. So the data is always persistent on disk. And now I quickly want to show you the generated files to give you kind of a flavor of what this looks like. Usually you will never yourself need to look at these files, but just to give you an idea of what we create. So you see here the code generation artifacts for my table. I created just a table, and you see here all the things that are generated on disk. So for example, the C file we generate as an intermediate step, the DLL, which is the final artifact of the compilation, and some other intermediate files, which we keep around mostly for supportability purposes. And if you look, for example, at the C file, you see your typical C constructs. We usually obfuscate the actual identifiers that the users give to prevent any kind of C injection attacks. Most of this will not be very intelligible, but you see things like serializing and deserializing rows for storage in memory, and also things like comparing keys to rows, comparing search keys to rows. So that's basically when you do an index seek, this function is used under the covers. Okay, now let's go back to Management Studio. And what I actually want to show you here is kind of a contrast of different ways to access this table and show you some of the aspects of how they differ. So first off, what I'm going to do is I'm going to, what is this? Sorry about that. I'm going to insert a number of rows. It's going to be 1 million rows, which I insert using an ad hoc batch. So I'm inserting these rows using interpreted T-SQL access. So as you can see, this takes a couple of seconds. This should take about 4 seconds. Yes, indeed. So it takes about 4 seconds. So keep that number in mind, because I want to, after this, I want to do the same operation of inserting 1 million rows using a number of other methods to kind of highlight some of their properties with respect to performance. Now, if I'm going to look at my rows in my table, if you look at the script here, you can see that I did insert all the rows in order. So I started with ID 1, and I went up to 1 million. So I inserted first row 1, then 2, then 3, etc. But now if I look at my rows, you can see they are not returned in order. That is because in a hash index, these rows are hashed to buckets randomly. It's a random hash function, which means the rows are just randomly spread out over the entire index. And when I scan through the index, it means that in effect, I get the rows back in random order. Or, well, semi-random, because every time I scan the index, it's going to be the same. So I always, when I execute this several times, I always get them back in the same order, but this is seemingly random. So as you can imagine, I can also not use this index for an ordered scan. I can only use it for like a full table scan, unordered, or for index seeks, point lookups. Okay. So of course I can always use an order by clause to get my rows back in order. Let me show you this a bit more. No, it doesn't really want to work with me today. Okay, there we go. So you see here, now they're of course returned in order when I ask for order, as usual. Of course, you all know when you want order, you should always specify the order by construct. Okay, let me go ahead and delete these rows. So what I'm going to do now is I'm going to do the same operation, insert the same 1 million rows using a natively compiled stored procedure. So I have here one stored procedure which has the exact same logic in it. So you see here, here's my loop, the while loop with the insert statements. So this is an exact copy actually of the T-SQL I had before. Let me go ahead and create this procedure. And now let me execute the same procedure. And as you can see, this is quite a bit faster. It's now under a second because I have all this logic inside the natively compiled stored procedure, and this allows me to execute the inserts much faster in a much tighter loop. And, well, of course, I have the same data, as you can see. So let me go ahead and delete the rows again. So the third method of inserting these rows that I want to show is, again, a natively compiled stored procedure, but slightly differently. Here I have a procedure that has only a singleton insert statement. So now, in fact, I'm not going to do as much work in a single stored procedure. Instead of processing 1 million rows in one procedure call, I'm processing only one, and I will have then 1 million procedure calls. So let me go ahead and create the procedure that inserts a single row. And then I have here my T-SQL batch that executes this stored procedure 1 million times. And as you can see, the execution takes a little bit longer than when you process a million rows with the same, within the same procedure call. As you see, this took about 6 seconds. Right. So what I want you to take away from this is that native procs are not magic kind of go fast buttons. No, you need to do a significant amount of work within the stored procedure to make it worthwhile. So in this case, actually the execution overall of inserting these million rows actually took even a bit longer than when I was not using any procedure at all. That is because changing the execution context between the interpreted T-SQL and the native proc has also some overhead with it. And because I did so many calls, did so many context switches, I end up with a less performance scenario. So the takeaway from this is you always need to think about what operations you are doing and whether you can get any benefit from using native procs. Now these were, of course, singleton inserts in a native proc, which is really very little work. So if you compare the work that a native proc needs to do compared with the work that interpreted T-SQL needs to do for an insert, there's not much difference if you talk about a singleton one. It's really, if you do multiple operations, if you do a lot of work, then the native procs really start to shine. So for example, if you consider the demo that we showed in the foundational session for SQL Server, where we had this jump from 7x to 26x by using native procs instead of memory optimized tables, we had each stored procedure processing 100 rows. So then the next topic I want to touch on, what you really need to consider for your applications, are the transaction semantics for memory optimized tables. So we have, let's say, the transaction semantics for memory optimized tables is quite a bit different than what you are used to typically from something like read committed isolation for disk-based tables. For disk-based tables, you use locking and blocking to guarantee isolation. Well, except if you use snapshot or read committed snapshot, then you do have some versioning, but still you use locking for writes. Now, a key aspect of transaction semantics for memory optimized tables is that it is multi-versioned. So the tables themselves have multi-versioning built in. As you can see from the table structure, each table can have like multiple versions of each row. They are just maintained inline as part of the structure, so it's completely built in. Second, all the transaction isolation for memory optimized tables is snapshot based. So every statement in your transaction sees a consistent snapshot as of the beginning of the transaction. No matter which isolation level you use, you always see a consistent snapshot as of the beginning of your transaction. And to implement this snapshot isolation, we use the versioning. So if you have, for example, a transaction starting at time 100, it sees all the rows that are valid at time 100. And because we have the versioning built into the tables, the snapshot isolation for memory optimized tables does not use tempdb, other than snapshot isolation for disk-based tables, which use tempdb for the versioned rows. For disk-based tables, you need to use a separate structure like tempdb to store your row versions, because you cannot just willy-nilly add and remove row versions in your pages, because you would have too many page splits and merges, and this would seriously degrade your performance. But because memory optimized tables are completely in memory, we can just, and rows are the atomic unit of storage, we can just add and remove rows easily to the in-memory structures. We don't pay any penalty for that. We don't need to do any splits or any merges or anything like that. You just add a row to memory, remove a row from memory. It's as easy as that. Well, the implementation may be a bit harder, but conceptually. Then the transaction semantics on memory optimized tables is optimistic. So the tendency here is that we always assume that operations will succeed. You always assume that a transaction is going to commit, because in all likelihood it is. If it fails at some point, okay, then you deal with the failure. But you assume optimistically it is going to commit, it is going to succeed. So we don't take any locks or latching, and also we minimize the context switching. So by doing that, we don't have any blocking. So we cannot have that a transaction takes a lock on some row and that another transaction needs to wait. No, we let the transaction just continue. And then, of course, the question is, when you let these transactions just continue, what happens when you have two transactions that try to write to the same row? In that case, there is a conflict, and this conflict is detected, and one of the transactions will fail. So in particular, you have one transaction which writes a row, another transaction comes in and wants to write the same row, but it sees that this row is in flux. It's already being touched by another transaction. So at this point, this transaction will fail, will return to the client with an error code, and the client will need to retry. Or you can have like a wrapper store procedure which does the retry for you. Now also, because we work like this, because when there is a conflict, you just fail, we cannot have deadlocks. Well, okay. Obviously, you would say because we don't have locks, you cannot have deadlocks. Well, I think more the underlying principle is when resources are not available at some time, when a row is not available at some time, we don't wait for it to become available, right? Either we read an older version, if we just want to read, then we use the snapshot-based isolation, or if we want to write to it and we see that the row is not available to write to it, then we fail, and we fail fast and retry fast. So we don't like waiting in the system. And then talking about snapshot isolation, there are a number of isolation levels that we support. So kind of the lowest isolation level we support is snapshot isolation. So with snapshot isolation, your reads are always consistent as of the beginning of the transaction. You always read from a consistent snapshot that existed when your transaction started. And writes are always consistent. Right? So if you write something, you know nobody else is going to touch the row because anyone else who wants to write to the row will fail. So writes are always consistent, will always succeed. Or your commit will always succeed if you write. Now the second isolation level, which is higher, strictly higher for us, is a repeatable read. So repeatable read gives you the same guarantees as snapshot isolation. So you always have consistent reads as of the start of your transaction. Your writes are always consistent. In addition, you get the guarantee that read operations, if you would repeat them at the end of the transaction, you would get the same results. So any row you read in your transaction does not change while you're running your transaction, does not change before commit. So you cannot have that you read row A and another transaction comes in and changes that row. No, if that happens, you actually have a repeatable read failure which you detect at commit time, and you will fail to commit at this point. Finally, serializable isolation. So in addition to the repeatable read guarantees, you have the guarantee that no rows are inserted that you would have seen. So if you do a scan, let's say you scan a full table A, and someone inserts a row in A before you commit, then at commit time you verify that no rows were inserted. If a row was inserted, you will fail to commit. So also you would better not scan full tables in your serializable transaction. Well, anyway, also if you have blocking semantics, you don't want to do that because then you may make the whole system wait. So in fact, in our case, with memory optimized tables, it is the transaction that requires the high isolation, like repeatable read or serializable, that will pay the penalty in terms of getting validation failures. Whereas With locking-based semantics, like for disk-based tables, there you let the rest of the system wait because you take a lock on your range of rows, for example, or your entire table. So here's a simple example of a write conflict. This can happen with any isolation level, so even with snapshot. So let's assume we have here two transactions. We have here T1 and T2. They both execute under snapshot isolation. And they attempt to update the same row. Now, in this case, transaction 2 was first. It wrote to the row first. Now, it writes the row, it marks the row as, hey, I'm updating it. And then the second transaction comes in, and we'll see, oh, hey, this row was already updated, so I cannot update it myself. So at this point, this transaction will fail. So you always have, with write conflicts, always the first writer will win. The second writer will need to retry the transaction. So we have a number of kind of general guidelines to work with these transaction semantics. First off, well, because we don't have any locks, we also don't support any locking hints. Now, many users use locking hints on SQL tables to get a certain amount of transaction isolation without having the whole transaction run under this isolation level. So for example, you need some kind of serializable isolation based on one row in a table. Then you take an X lock on that row. So you say, hey, I want to run this operation with X lock. And then you kind of guarantee that nobody else will touch that row during your transaction. You cannot do that with memory optimized tables. You need to always declare which isolation level you need. So in this case, you would say, I want my transaction to be serializable. Then you need to be mindful of the conflicts and validation failures that can occur. So the write conflicts and repeatable read and serializable validations that can occur. Whenever these occur, you will need to retry the transaction. This is fairly similar to the retry logic you already need for deadlocks. However, we are aware that not everyone implements retry logic for deadlocks, either because they write their apps such that there are no deadlocks, or they are sufficiently rare that it is not necessary to catch them. But in typical applications that use memory optimized tables, you will find write conflicts, if not validation failures. Although you can also write your apps such that these do not occur, if you are very careful. But we do recommend, typically, to use retry logic, for example, using a wrapper store procedure. And you also want to avoid long-running transactions. There are two reasons here, three reasons actually. The first of it is, of course, always bad to have long-running transactions in your system because they always hog resources. So even for disk-based tables. But then especially for memory-optimized tables, this becomes problematic because this transaction is going to be old at some point, but will still potentially need some rows that are some old rows that were in the system when the transaction started. Because it is snapshot-based, all the rows that existed as of the start of this transaction will need to be kept in the system. So it will hog memory. It will start using a lot more memory. And third, you can have a write conflict or validation failure occur at any point while the transaction is running. And if it occurs after the transaction has been running for a long time, then there's a lot of work you would potentially need to throw away. And you would need to redo all this work, so better to avoid them. Then another concept I want to talk briefly about are cross-container transactions. Now, cross-container transactions occur when you access both disk-based tables and memory-optimized tables in the same transaction. Why do we call it cross-container? Well, you can view like SQL Server as having two containers as far as transactions are concerned: the disk-based container and the memory-optimized container. And each container, you have a transaction context. Let's say you have here a regular transaction context and here a memory optimized transaction context, right? Because the transactions are handled differently. Now, if you want to access both disk-based and memory optimized tables in the same transaction, you will get a cross-container transaction, which brings together a regular transaction context and a memory optimized transaction context. Now, as you can imagine, because here logs are used for guaranteeing isolation, and here we use versioning and conflict detection for isolation, that is not that easy to marry these transaction contexts and give the right isolation guarantees for the transaction as a whole. Therefore, we do have some restrictions on isolation levels that you can use. So these are the combinations of isolation levels that we do permit. So you can view this like, okay, you use one isolation level to access your disk-based tables, and you use one isolation level to access your memory optimized tables in the same transaction. So the first combination is if you use read committed for your disk-based and snapshot for your memory optimized tables. So first off, read committed isolation is not supported for memory optimized tables. We always have a snapshot as the beginning of the transaction. So therefore, you cannot use read committed, of course, for memory optimized tables. But this is the kind of baseline combination. So if you use read committed isolation for your transactions today, then we recommend to use this combination in your cross-container transactions. So read committed for your disk-based tables, snapshot for your memory optimized tables. And if you want to go a bit higher, you can go a bit higher on either side, but not on both sides. So you can say, I want to get repeatable read or serializable isolation on my memory optimized tables, or you can say I want repeatable read or serializable on my disk-based tables, but you cannot get it on both. That is, unfortunately, a limitation that we have at this point. But there are some scenarios in which you could think that these combinations are useful. For example, if you do some kind of data migration, or also if you have transactions that use interpreted T-SQL access to access only memory optimized tables, then also this combination would be useful. So what we don't support is, first off, if you have repeatable read or serializable on both sides, we cannot support that. And also, if you want to have snapshot isolation on disk-based tables, we cannot support that because the timestamp and versioning mechanism for disk-based tables is different than that for memory-optimized tables. At this point, we don't have any effective means to synchronize these mechanisms, so you cannot use it in a cross-container scenario. You can, however, use read-committed snapshot for your disk-based tables. So now I want to show you some aspects of this transaction semantics. Through a short demo. So I want to contrast the behavior. Oh, sorry, I need to switch here. So I want to contrast the behavior that you get for regular disk-based tables in the read-committed isolation level with memory-optimized tables in snapshot isolation. So for comparison purposes, I'm going to create a disk-based version of the table that I had. So my sales orders table, this has the same schema as my memory-optimized table. And I'm going to insert a number of rows in it. Now, because I want to run two concurrent transactions, I'm going to open the second script next to the first one. And the first thing I want to do is now I want to start a transaction on my disk-based table, and I want to do an update in that transaction without committing it. So I have here my statement. I'm going to update row 1 and set the order status to 2. But I have not yet committed my transaction. So now, in a concurrent transaction, I want to read this row, read row 1. Now what happened is that my first transaction actually took a lock on this row, which prevents my second transaction from actually reading this row. So my second transaction is blocked and will need to wait for my first transaction to finish. So if I now start execution of the statement, after I change, of course, my database to the right one, so I start execution of the statement, and you can see it is now waiting. It says it's executing the query, right? But it is blocked. It is waiting for the lock on this row to be freed up. If I now commit my first transaction, you can see my second transaction now becomes unblocked and returns the row with the updated state, with the updated order status number 2, which I just set in my transaction here. So it waited for the first transaction to finish and only then read the row. So it reads the new version of the row after the transaction commits. Now if I do the same thing with a memory optimized table, I start a transaction and I update a row. Now what happens is that I write a new row version, but I keep the old version around for anyone who wants to read it. My new row version is of course not yet visible to anyone because I have not yet committed my transaction. So if I go now in my second transaction and I want to read this row, then I get my result immediately and I get, of course, the old order status 1. Right? And now, if I want to actually update the same row, so I can read this row, as you can see. I can read the row I was just updating in a separate transaction. So writers do not block readers. But now I want to update the same row in a second transaction. So we don't want this to succeed because this would make the database inconsistent. So what happens is I get an error message, and my transaction is terminated in this case. So the error message reads, the current transaction attempted to update a record that has been updated since this transaction started. So I detect a conflict and I abort my transaction. But my original transaction is untouched, so I can simply commit my original transaction and I can now see the new state of the database where my order status is number 2, which is what I just set it to in the transaction that just succeeded. So these are basic write conflicts, basic blocking versus write conflicts. Second thing I want to show is a scenario where with a disk-based table you get a deadlock, and with a memory optimized table you get a validation failure. So, and this is a very typical deadlock case. So I'm going to read a row here under repeatable read isolation. And so I'm going to read, with my transaction 1, I'm going to read row 2 under repeatable read. So I'm going to take a lock on this row. So let me go ahead and take a lock on this row. Starting my transaction, read this row, and because I use repeatable read, I take a lock on this row. Nobody else is allowed to touch this row. Now my transaction 2, I'm going to also, under repeatable read row 1. So transaction 2 says nobody else is allowed to touch row 1. Now, in my transaction 1, I actually attempt to update row 1. And because my transaction 2 took a lock on it, my transaction 1 is now waiting. It is blocked. It will wait until this resource is freed, until the lock is freed, and it can do something. However, in my transaction 2, I'm now going to say, hey, I want to update my row 2. But row 2 was locked by transaction 1. So we have now a typical deadlock situation. And as you can see, what SQL Server does, it detects the deadlock, and it will choose a victim, choose a deadlock victim, and terminate that transaction. So we see here that this transaction was deadlocked on resources with another process and has been chosen as the deadlock victim. This transaction was fine. I can now commit it. And as you can see, if I try to commit this transaction here, mean, I already don't have a transaction anymore because it was aborted due to the deadlock. Now, when I consider the situation with memory optimized tables, I'm going to say, hey, I want to read this under repeatable read row 2 with my transaction 1, and read row 1 in transaction 2. So what happens is I don't take a log. Right? I just remember, hey, this row, I don't want this row to change during my transaction. And now with my first transaction, I want to update row 1, and this actually succeeds. So within this transaction, I updated my row. I updated this row, even though another transaction wants repeatable read on it. Similarly, my transaction 2, I can update row 2. And now I attempt to commit my first transaction, and this actually succeeds. So no waiting, it just succeeds. And remember, I wanted to have repeatable read on this row 2, and indeed, this row 2 has not been updated in the database because no transaction has committed that changes this particular row. But now, if I want to want to commit my transaction 2, then we have row 1. I wanted repeatable read for this row 1, but row 1 has been updated in a database already by my transaction 1. So this means I'm not allowed to commit. So if I try to commit, you see I get a validation failure, a repeatable read validation failure. Okay. So that is the kind of basic overview of the transaction semantics, things you want to keep in mind. Of course, I don't have too much time to go into too much detail, so please feel free to ask me any questions afterwards. Just to recap the main things I touched on here. So first, memory optimized tables and indexes. So they are natively compiled on start. And we have a new type of indexes, hash indexes, which are particularly good for point lookups. And point lookups are also typically used in OLTP scenarios. But we do have ordered indexes, which are useful for range scans and for ordered scans coming in CTP2. The data store itself is multi-versioned. Then to access memory optimized tables, we have the interpreted T-SQL access and the natively compiled stored procedures. Where the interpreted T-SQL access, you have virtually the full T-SQL surface area. Natively compiled stored procedures, you have a limited surface area, but potentially very high performance gain due to much more efficient execution of your business logic. And then transaction semantics. So we have new transaction semantics, which is multi-versioned and snapshot-based. So you always read the rows that are valid as of the start of your transaction. And it is optimistic, so we don't use locking, but we use conflict detection to find any problems in potential consistency issues between transactions. And finally, for cross-container transactions, you need to be mindful of the limitations that we have. So as for related content, there's tomorrow still a session on DBA concerns for memory optimized tables, where I will go into more detail about memory usage and storage formats, what we do exactly with checkpoint files, what the memory looks like, how to manage these things. And there's also a hands-on lab. You can always find me after the session. There's going to be the Ask the Experts, and also I will be at the booth. Resources, you've seen this. Please fill in your evaluations. I heard that not too many evaluations are filled in with this TechEd, so I do encourage you to take some time to fill in these evaluations. I don't think we have a lot of time left for Q&A, but if you have any further questions, please feel free to come up after the session or find me at any time later at the conference, at the booth. Okay. Thank you.